I want to look at an additional data example too, maybe a more realistic data example. The main effects in the dogs running the obstacle course example were reasonably different from each other because I made sure that the sample sizes were different from each other. But in most real-world cases, they won't be so dramatically different. So let's go back to the robots example. And here I'm just using the read.csv function to read a version of the robots CSV file that I have already prepared. And you can see the previous videos for an explanation of this example dataset. It's the same one that I used in the regression interactions video and some of the prior videos as well. I'm going to set up reference categories for the material factor and the transport factor. So the material factor will be set up so that plastic is the reference category and metal is the other category. And the transport variable will be set up so that wheels is the reference category and the robots with legs get an indicator variable. And then I'm going to run the summary function on the output of the LM function with this model formula. Price is the response variable, and I have material and transport two factors interacting to predict price. There is a statistically significant interaction. The metal robots are more expensive than the plastic ones when they have wheels. The robots with legs are more expensive than the robots with wheels when they're made of plastic. And we know that both of those things will depend on the value of the moderating variable. Let's suppose that you already know how to get the conditional association between metal and price for legs and wheels separately, and the conditional association between legs and price for metal and plastic separately. But now we want to practice getting overall main effects for both of these variables. First, I'm going to look at the no interaction version of the overall main effects. I can fit a regression model that simply has a plus sign rather than an asterisk between material and transport. This is a version of the regression model that has these two main effects and no interaction. And I get estimates of the main effect of metal and the main effect of legs adjusting for each other. Here's the regression model that has the interaction again. And to understand what's going on efficiently here, I might call the capital A ANOVA function from the car package on the full model that has the interaction to get tests of the main effects of material and transport in a model like this one that just doesn't have the interaction, in a table alongside a test of the interaction that is equivalent to the test of the interaction from this regression summary table. This is what I suggest doing. It's the easiest and most sensible approach, or at least the easiest and most sensible default approach to trying to get overall main effects when your primary analysis model includes an interaction. But let's do the contrast-coded version. This time I'm going to set up my contrasts by assigning a new matrix to the contrasts attribute of the factors included in the model. So first I'm going to assign to the contrasts of material a new matrix that has -0.5 and 0.5 as its values. And I'm going to assign to the contrasts of transport a similar new matrix. The result is that these are the contrasts for the material factor at this point. There is one contrast, and it has plastic coded as -0.5 and metal coded as +0.5. And there is one contrast for the transport factor. It has wheels coded as -0.5 and legs coded as +0.5. Now, if I include these factors in a regression model the normal way, I know that these contrasts are getting used. So the reference point is precisely between the two categories of each variable. And 9.69 represents the price difference between metal robots and plastic robots, at a point precisely between what that price difference would be if they had legs and if they had wheels. And 5.70 represents the price difference between robots with legs and robots with wheels, at a point precisely between what that price difference would be if they were made of metal and if they were made of plastic. And I can get f-tests consistent with this kind of regression summary output by plugging this regression model into the capital A ANOVA function from the car package specifying type equals 3. These f-tests are equivalent to these t-tests you can see that they have precisely the same p-values. This is what SPSS does when you use the default univariate ANOVA function. I also want to show you how to do this with centered versions of indicator variables. But first, I just want to set the standard representation back for my binary factors, so material and transport will have their usual contrasts, because I don't want to keep them this way. It'll confuse me later if they're negative 0.5 and 0.5. So I'm going to use the relevel function to set the reference category for material to plastic and the reference category of transport to wheels. And now we're back to the typical kind of regression model where the 16.96 represents the difference between metal and plastic for the robots with wheels, for example. By the way, if I create numeric versions of the material and transport vectors so that robots $metal is the numeric equivalent of the test whether material is equal to metal, so that all of the metal robots will have 1 and the plastic ones will have 0, and robots $legs will have all of the legged robots with 1s and the wheeled robots with 0s. I can plug those new binary variables directly into my regression model and get output that is precisely consistent with what I got when they had the factor encoding and the indicator variables were generated for me automatically. Now I'm going to create centered versions of these indicator variables. But this time there's missing data, and I know that there's missing data. So I need to be a little careful when centering these variables, because centering involves calculating the mean of the variable, and the mean of the variable might depend on which cases are included. I don't want to use a mean that has extra data in it that won't end up being relevant to my regression model. So I'm going to create a vector called model subset, which indicates which cases are complete for these columns of the robot's data frame: price, material, and transport. Then I can use that model subset to calculate the mean. And again, I don't need na.rm equals t, because I've already guaranteed through the use of this subset that there are no missing values. But otherwise, I'm doing the same thing I did before. I'm creating metal centered, which is the result of taking the metal indicator variable and subtracting its own mean, but the mean calculated only from those cases that are going to get used in the regression model. And I'm creating legs centered by taking the legs binary indicator variable and subtracting its own mean from the subset of cases that are going to be used in the regression model. Then I fit that regression model with those centered indicator variables and price as the response variable and get the summary. And here I have the other kind of main effects. These are estimated not at the precise midpoint of the values of the moderating variable, but rather at the mean of the values of the moderating variable, somewhat closer to whichever group of the moderating variable happens to have slightly more cases in it. And I can call the ANOVA function from the car package with type equals 3, using this regression model as its argument, to get an ANOVA summary table with f-tests that are equivalent to these t-tests right here. So that's how you get f-tests consistent with the 3 different types of main effects that it's possible to define in a regression model that has an interaction term in it. But remember, there is a perfectly sensible default that you can use. If all of this stuff about type 3 seems like a lot of information, you'll be fine if you just do it this way. Here is a regression summary of a model that has an interaction term in it, and I plug that same model into the capital A ANOVA function from the car package with no special type argument, using the default type, which is type 2. And I get a summary table that has 2 reasonable default main effects and an interaction in it. Don't forget that this is the capital A ANOVA function from the car package, though, because it will not work if you use the lowercase a ANOVA function from base R. It might look like it works, but it's not providing the same thing that this function is providing.